So these are the creatures that it all starts out with, just randomly made creatures.
What are these creatures?
They're virtual creatures. They're virtual entities that can move and behave in a simulated world of physics.
What's virtual?
Virtual, in this case, is digital. They're all in simulations in a computer.
And what is the world like that they live in?
It's a world of simulated three-dimensional physics. And so it's a world that's meant to be at least somewhat like our real world. I designed a genetic language, a genetic code like DNA, except a virtual version of this, so that in the computer you could represent the genes of a creature, and then the computer could grow a virtual creature from those virtual genes. So it's setting up a genetic system with which to describe these creatures. And then you let these creatures evolve by reproducing and by selecting for certain types of creatures, and that's how the more complicated creatures are created. So this shows the evolutionary history of a swimming creature, the segmented flipper strategy. The first one just is a couple blocks that might have twitched slightly, but it twitched a little better than all the other ones, and so it survived and reproduced and made more like it. And then it developed a single flipper that could flip, and then it duplicated that flipper to make two flippers. And then once it got this flipping ability, it started making more and more flippers so that it could go faster and faster. So then it got 2 segments, which gave it 4 flippers, and 3 segments, which gave it 6 flippers. And it may have kept going, adding more and more pieces together, getting more streamlined with more and more flippers. And this is that same final water snake with his corresponding brain that instructs his muscles how to move. One thing that's interesting to notice about these virtual brains, which have evolved, is that they're quite difficult to figure out and understand. And even if you know what all the pieces are and what they do, it's hard to understand how the whole brain gives the behavior that these creatures have. It's hard for me to figure it out. Given a lot of time, maybe you could figure it out, but it's not easy. But when you're evolving creatures, when you're using this technique, you don't have to understand these things at all. You can just let them evolve. They're complicated brains that give them various behaviors without ever having to even see these diagrams. So it allows us to go beyond what we can design. If I were to try to hook together these sensors and neurons and effectors myself, I might never come up with a good solution that could make this thing swim. But evolution can still do it.
So it's like nature. You don't understand it.
Right. In a sense, it is. This tape shows a number of creatures that resulted in simulated evolutions. It shows the results after a number of generations. Here's some that are evolved for swimming ability. Here's a number of different strategies that came up. Here's one that swims with a flagellum-like tail. Here's another one that is kind of kicking itself along. Some of them look like real-world creatures a little bit, but others look completely different from things that you see naturally. Here's a water snake-like creature which actually does helix motions a little bit. And then here's another water snake type of strategy, and 3 of them in the same simulation. So now these are given land physics, friction and gravity, and selected for their ability to walk. And some very simple strategies came up which could still propel the creatures across the ground. Some with counterweights that just swung, and others with 2 leg-like appendages that can flip over each other. Here's one that has kind of like a rowing strategy, and he can go quite quickly along the ground. This is a relative of that creature that has a slight variation in his gait. Every stroke he does a somersault and then continues along. There was no selection against dizziness for these creatures, so that was a perfectly good solution. This is one that is like an inchworm type of strategy. That a number of things came up that were a little bit like inchworms. This one was actually the water snake that I put on land and then let evolve further to see if he could sidewind or whatever. And sure enough, after a number of generations, he figured out how to crawl. And he can even crawl in two directions. There, he tipped over a little bit and then started pushing from the other side, which is, it seems fairly complicated how he would know to do that, but sure enough. And here's one that kind of bounds along with two leg-like appendages, and this is one of the faster creatures on land. Here's another group of creatures which were selected for jumping. So the higher they could get off the ground, the better they were rated and the more that they survived and reproduced. So the final challenge for these creatures was actually to compete against each other. Natural evolution doesn't have anybody saying what fitness is. There's no definition of who gets to survive and reproduce.
Like you say to these simple creatures that swimming is good.
Right. So that's, in a sense, that's optimization. You know what the goal is, and you're trying to optimize towards that particular goal. And I gave them these goals. The goal was the only thing that I gave them. They figured out the solution, but I still gave them the goal. Now, natural evolution doesn't even have that goal. The fitness depends on a lot of other things that are evolving, other creatures in the environment that are evolving, changing conditions in the environment, all affect what fitness really is. And so there is no such thing as a goal or a definition of fitness. And so to simulate natural evolution a little bit closer, I thought that a competition situation would accomplish that. So the world has a desirable cube in the middle, a common resource. Perhaps it represents food. And one creature starts on one side of the cube, another creature starts on the other side, and then they are let go to perform their various behaviors, whatever they might be. And the one that is closest to the cube at the end of a certain amount of time is the winner.
It gets the food.
Right. And that means that it gets to reproduce and make more offspring that are copies but with mutations of itself. Here's these creatures which figured out how to roll towards the cube. And at first they both just would get to the cube and touch it, so this was a tie score. A few more generations later, though, a strategy came up which would not just get to the cube but shove the opponent away. And so that was winning for quite a while. More generations go by, and this one evolved to deal better with this offending arm, and it learned how to climb up and over it to still get to the cube. Here's one that, an arm-like strategy that knocks the cube to the side and then pins down his opponent. But that arm doesn't do very well against some of the other ones that cover up the cube quickly. Here's some more arm-like things which kind of fall over onto the cube. Some unfold and some take a few steps first. This one got lucky and sneaks in between the two cover-up fins that cover it up, so he wins that. Here's one that can walk with one leg and actually bat the cube away and take it far away from his opponent. So this one was winning by a large margin because he could take it so far away. Here's two of that same strategy going against each other. And I actually ran this simulation for longer than it was supposed to go because I was curious who would win in the end, because they seemed to really be battling it out. And eventually the one with the thicker hand got away with it. Here's an arm that actually jabs his opponent and then curls around the cube to block it. And that was a very successful strategy. This one figures out how to walk quite nicely, but he's not adaptive and doesn't stop when he reaches the cube, and he keeps going, and he seems to be more interested in beating up on his opponent than actually sticking with the cube. Then this strategy came up where things sweep in from the side and quickly get the cube under control. And that strategy was doing very well. Again, the crab doesn't know what to do in this case. Here's two of these similar strategies against each other. And this one got to it slightly faster than this one and ends up winning. So again, this blue one is won that competition. Here's the seeker arm that can adaptively follow it. And he's trying to reach the cube, but it pushes it slightly out of reach. And he goes into oscillations because it's out of reach.
Where is this all going to go to?
Well, one thing that I would like to do is, instead of giving them a simple world that's defined and set up, and having only one or two creatures in the world at once, I think it would be interesting to make the entire evolutionary process all in one physical simulation. So the creatures are all running around together with their children and relatives, and then you could have more different types of things occur, such as cooperation and communication between creatures, and perhaps some social systems could evolve. And there's just a lot of potential for the results if you just let it happen instead of defining the goals or even defining a competition.
But you think that they'll evolve spontaneously, all that?
Eventually, carbon-based thinking and bodies will become less and less important. I think we will replace the human body just as we're going to replace the human brain with methods that are built on similar principles, but that are more powerful and that overcome some of the limitations of the human brain and body. The real relevant cutting edge of technology, cutting edge of evolution is our technology, and it's going to move in the 21st century towards hybrid human-machine, new forms of beings that are far more intelligent, far more creative, far more capable of creating beautiful things than humans are, and that's the next stage of evolution.
This is my brain, my artificial brain. And I believe this machine is the beginning of a technology that will have more impact on humanity in the 21st century than the development of the hydrogen bomb.